The objective of this video is to run a demo to show one can use Numba to accelerate their Python code-based motor control simulation. This is the outcome. There are basically 4 steps in this video. Step 1, we need to install the Python program from this website and make sure you check this add Python 3 to pass checkbox, and it will allow you to call pip from your command line. But Python 3.10 does not work well with Numba, so we need to install 3.9 instead. So make sure when you are downloading Python, you are installing Python 3.9. But the problem here is that I have already installed Python 3.9, so I will need to create a virtual environment for this project. In this case, I pretend I have a new Python distribution installed, so I will need to also install Numba and matplotlib. Okay, you don't need to. While it's still installing, we should be able to download the code to local. So use any method you like to you can download the code from this repo. So I will simply download the code here. Okay, now open your Visual Studio Code. I will close folder, and I will pull the downloaded codes folder to the VS Code. And I open main.py, then I can just run the cell. The shortcut is Shift-Enter. But apparently it does not work because you need to specifically tell your VS Code which Python distribution you are using. So we are using Numba demo, so we are going to select that. Okay, then Shift-Enter. Okay, it requires you to install IPyKernel, so you just click install. Okay, now I think we are good. Shift-Enter. Okay, it's connected. So the first cell, it compiles the code. Okay, we have more errors. We cannot import the name JIT class phone number. Also, there is a change. Something changed. So basically, we need to do something like this. So you open acm-simpy.py file and number.experimental import JIT class. Okay, then open main.py and Shift-Enter. Okay, now it's compiled. The code is compiled by Numba. So next time you run the same code, acm-simpy, it will be faster. Okay, here is the outcome. The first figure shows your ID and IQ of your controlled motor, and this I think is I alpha and I beta in the alphabet reference frame. And finally, this is the speed, motor speed in revolution per minute. Now let's take a look at the code. At line 2, we import everything from this file to the main.py. And we also need to import time. We are going to measure the execution time of our code, which will be 1.05 seconds. At line 4, we compile this code. So this will be a function that's decorated by this njit decorator. When this function is compiled by Numba, we are ready to we are going to call it for solving much more steps. So with more specifications, the range of our x-axis will be 5.5 seconds. Our machine sampling time will be 1e minus 4. Our current loop sampling time will be 1e minus 4 as well. And the output of this function will be a watch variable, so which is a tuple of different arrays, and those arrays will be plotted for plots. So let's take a look at this function. In this function, step 1, we need to declare our array variables. Step 2, we need to initialize our JIT class. And you can take those state class as some structure for storing different data. In our case, we are going to have one variable for AC machine, one variable for controller, and more variables for our DQ current regulators and speed regulators. Of course, we need to specify the KPKI coefficients for PI regulators. Then the third step is the main loop in this machine simulation. First, we will take a time from our machine times array. We are going to pass this T and ACM variables along with the machine TS parameter into a numerical integrator called RK4. Then we are going to execute our controller at a reduced sampling rate. But in this simple demo, the execution time of our machine simulation is equal to our controller's execution frequency. Inside the controller, we need to first convert our ACM states into alpha-beta frame. This is because our ACM is simulated in the synchronized DQ frame. So x0 and x1 will be ID and IQ. We need to convert them to I alpha and I beta. And in reality, we do not have access to ACM variable. We only have access to control variable. So we are going to pass our machine state to our controller's measurement results. This will include our theta d, the d-axis position, and motor electrical speed, and our I alpha, I beta current. Then we are going to do a path transformation to convert measured I alpha, I beta to ID and IQ. This is not related to our controls. This is simply to store some variables for later watch or plot. Finally, in our main controller codes, we are going to implement something called ID equal to 0 control, and we are going to pass our speed command in this function through the control variable, and the speed command is dependent on t. Finally, our output voltage command in alpha beta frame will be converted to DQ frame, and this DQ frame voltage will be used in next step of numerical simulation of our AC machine. And after the main loop, we will return a tuple of our watch variables for post-processing. Thank you for your time.